All right, so welcome to Math 150, Section 1, Lecture 2, Section 1, Lecture around 8, maybe 8 times, 2021. And so what we're going to do today is we're going to talk about optimization. This is one of the best applications of multivariable calculus. I am trying a different mask today to try to figure out which mask allows the best recording possible. So if you're listening to this at home and you want some say, let me know how it's going. Before I do that, there were two problems people wanted me to talk about. The first was a limit problem. And so it was the limit as x, y, z goes to 1, negative 1, 1, and then it was yz plus xz plus, I'm going to get xy, all divided by 1 plus xyz. So when you see something like that, what limit law would you love to use? Your hope would be you can use the. So if you listen, the math is always trying to speak to you. It's trying to tell you what to use. Does this look like it's going to be a sum law? What law does it look like it's going to be? Quotient. We have a quotient. So your default should be, can I use the quotient rule to handle this? Well, I need two things to happen to use the quotient rule. The first is the limits must exist. If the limit doesn't exist, I'm not going to be able to use it. And the second is the denominator can't be 0. So if we look at the top, what happens as x, y, z goes to 1, negative 1, 1? So the numerator goes to negative 1 times 1 plus 1 times 1 plus 1 times negative 1. And what would that be? So it would just be negative 1. And in the denominator, goes to 1 plus 1, negative 1, 1. And what does the denominator go to? 0. So can we use the quotient rule? No, the limit doesn't exist. As we get closer and closer and closer to the point 1, negative 1, 1, the top gets closer and closer and closer to 1, which is great, but the bottom gets closer and closer and closer to 0. So the limit does not exist. We often write D and E for does not exist. What if I just had x, y, z in the bottom and not 1 plus x, y, z? Would the limit exist then? Yeah, then the denominator would be going to negative 1, the top would be going to negative 1, it would be going to 1. And so everything would be fine in that case. Okay, any questions about this?
I was talking about whether you can say that it goes to negative infinity.
So one of the problems with that is, in terms of does it go to negative infinity, a lot of it is, if x and z are both 1, and y is a little bit less than negative 1, this product here will be a little bit less than negative 1. And so the denominator is now going to be a very small positive number. Conversely, I just realized I misphrased. What's a little bit less than negative 1? Yeah, so I went the wrong direction. So if this is a little bit below negative 1, then this whole thing here would be a little bit below negative 1 when I multiply, and the whole denominator would be negative. If this is a little bit above negative 1, like 0.9, 0.99, 0.999, then this whole thing, when I add it to 1, would be a small positive number. So it's not going to go to negative infinity or positive infinity. It can alternate between the two. If I were to square the denominator, then you could say it goes to infinity. And you can get into a philosophical discussion as to, do you allow infinity to be a limit point? Do you allow to say it's converging to infinity? I'm quite fine with that. It's getting larger and larger and larger. I'm happy if you want to say the limit exists and is positive infinity in this case. But in the other case, when it's alternating between plus and minus infinity, then the limit doesn't exist in that. Okay. Any other questions on this problem? So the other question was talking about finding the highest point on the surface. And before we get there, I want to just talk a little bit about how to find maximum and minimum. So if I give you a function in one variable calculus, how do you find its maximum and minimum? Yes. Thank you. So critical points, those are where f prime of x equals 0 and the boundary. I often ask people to say, if they don't mention boundary points, where am I running the fastest? And then I start speeding up as I go near the blackboard. And so I'm clearly not moving my fastest at an interior point. So a lot of these tests, they're designed to give you candidate points. Hopefully you only have a few candidates to check. The more candidates you have, the more work there is. If I give you an interval, how many boundary points are there? So how many boundary points are there to worry about? 2. Is that a big deal? It's not a big deal to check just 2 boundary points, right? What if there were 3 or 4 boundary points? Is that a big deal? No. What if there were infinitely many? Is that a big deal? Yes. And so when you consider how this might extend to several variables, now all of a sudden, if I have to find the maximum and the minimum, I have to check the interior, and now there's infinitely many points on the boundary. I need a better way. It is fundamentally a different game in several variables than it is in one variable. And we need more powerful techniques. And so we're going to see something called Lagrange multipliers, and we'll get into them in greater detail later. What do you think might play a role in understanding where a function of several variables has a maximum min? So what object have we looked at associated to a function that might have some role to play? The derivative. So in one variable, if I give you f prime of a, that's the limit as h goes to 0 of f of a plus h minus f of a over h. And imagine, so I don't think anybody has seen plots like this. They've gone out of fashion. You plot the x-axis, and below it you plot f prime, and below that you plot f double prime. And I'm going to just put down the signs of it. So the positive signs means that f is positive in that region. F prime is positive in that region. But what does that mean? If h is a small positive number, the denominator is positive. If f prime of a is positive, and the denominator is positive, what must be true about the numerator? Positive. So that means if I go a little bit to the right, my function goes a little bit larger. What if I go a little bit to the left so that a plus h comes before a? That means h would be negative. So if h is negative, but the whole ratio in the limit is positive, what must be true of f of a plus h? How does it compare to f of a? So if it's bigger, then the numerator would be positive and the denominator would be negative. We're assuming that the first derivative is positive right here. So it would have to be negative. So f of a plus h has to be less than f of a if we go a little bit to the left, if we want f prime of a to be greater than 0. So that means the function has to look like this. So in a small neighborhood of a, if the first derivative is positive, it tells you you look like this. That means you're increasing as time goes forward, and you're decreasing as you go backwards. Think of it as you're running with a positive speed. If you're running with a positive speed, can you be at your maximum or your minimum? Unless you hit the boundary. If I hit B, it's okay if my first derivative is positive. Saying if you let time go further, you'll be even higher. Okay, but I'm not allowed to have time go further. I'm stopping at B. So that's why you have to check the boundary separately. But as long as you're not at the boundary, if the first derivative is positive, wait a little bit more and you've gone further. Go back a little bit and you haven't gone as far. So if the first derivative is positive, do we have a max? No. So if f prime of A is greater than 0, no max or min at A. But what if f prime of A was less than 0? It would be a similar argument, except instead of increasing to the right, it would now be decreasing. So also, no max or min at A. So, if f prime of A equals 0, have a max or min. Is that a correct conclusion? If the first derivative is positive, it's not a max or min. If the first derivative is negative, it's not a max or min. So if the first derivative is 0, it's a max or min. Now, what can I conclude?
If you have a max or min, then it should be.
Yeah, so if I have a max or min, then the first derivative is 0. So you can say have a max or min candidate. So the best function to look at is f of x is x cubed. F prime of x is 3x squared. F prime of 0 is 0. But if you plot the function, it doesn't have a max or minimum at 0. What goes wrong is that the second derivative is also 0, and that's what's screwing things up. It's not just the first derivative. If the second derivative is not 0, then we have the second derivative test. And we can tell if we have a max or minimum. But if we just have the first derivative 0, we don't have a max or min, we have a candidate. The hope is that we don't have too many candidates. So much of the world is trying to optimize things. Imagine you own American Airlines. What is your objective? Maximize profits. Your objective is not to fly people. How do you maximize profits? Hopefully by flying people efficiently. And this is one of the reasons why you don't have as many direct flights between cities as you used to. You have a lot more of the hub system. So we want to find candidates for maximum minimum. And so in one variable, we have a huge theory about how to do this. And so you have the first derivative test. So let's say here is f prime, and the first derivative is 0 at some point. And imagine it looks like this. Well, if I want to plot this, this is telling me my function is increasing up until I get to the critical point, and then it's decreasing afterwards. What must I have? A max. And if it was the other way, what would we have? Min. A great way to remember this is there's some way to determine if I have a max or min by looking at the first derivative. Let's look at a of x is x squared, which is probably like this, and b of x is negative x squared, which is a parabola like this. One of them is the max, one of them is the min. It's not that hard if I actually give you the parabola to look and see, oh, okay, this is the minimum, this is the maximum. I can then calculate the derivative and say, oh, okay, here the derivative is going from negative to positive. This is going to be, this case is going to be a min. So if you can't remember the first derivative test, if you can just remember, check the parabolas x squared and negative x squared, you can actually rederive the test. This also leads to the second derivative test. So if f prime of a equals 0 and f double prime of a is greater than 0, we have a min. If f double prime of a is less than 0, we have a max. What case am I missing? Right, and so what do you think you would have to do if f double prime equals 0 as well? Go, that's not fair. No. As fun as that may be, what would you do if the second derivative is 0? Well, do what again? Take another derivative, right? And this would give us the third derivative test, right? And so you should be able to keep taking derivatives, and hopefully eventually one of the derivatives is not 0, right? So over here, let's try to think what's going on. So here's x, here's f prime, here's f double prime. So this method is no longer taught anymore, which I think is a real shame. It's a really nice way to see what the curves look like by doing a little bit of graphing. So I have some special point A, and I know the first derivative is 0 at A. And I'm going to assume f double prime of A is positive. Okay? Well, if my function is continuous, my second derivative is continuous, what must be true about the second derivative if I'm close to A? If it's positive at A, what must be true close to A? It's also going to be positive. So in some neighborhood of A, it's going to be positive. If the derivative is positive, what does that tell you about the original function? So what about the slope of the original function? So what is happening to my original function if its derivative is positive? It's increasing. Who has f double prime as their derivative? F prime, right? F double prime is the derivative of f prime. The derivative tells you something about the original function. So f double prime tells us about which function? F prime. This is like the acceleration in physics tells you something about the velocity. So if I know that f double prime is positive, what must be true about f prime? It's increasing. Right. There's a difference between positive and increasing. So if f double prime is positive, that means f prime is increasing. Well, if I'm 0 here and I'm increasing, what must be true a little bit before 0? What must be true about f prime? No, it's negative. So f double prime is positive means f prime is increasing. I'm increasing up to 0. So if I'm increasing up to 0, I've got to be negative and I'm rising to 0. So f prime has to be negative a little bit before A. Because f double prime is positive, what's true about f prime a little bit past A? Positive. So now you know f prime goes negative 0 positive. Does that remind you of anything on this nice, beautiful, clean blackboard that has not been erased yet? Yeah, it looks like this thing right down here, negative 0 positive. So the first derivative is coming down. First derivative is negative, so my function is coming down, and then starts to come back up. Now, so I know my function has to look something like this. And so that's why if the second derivative is positive, you have a minimum. You can do a similar proof if f double prime is less than 0, or if you want, just let the function g of x be negative f of x, and then we'll switch all the signs. And then the minimums become maximums, maximums become minimums. But you can go through the same argument all over again. So this is the first and the second derivative test from calculus. They're really nice, they're really easy to use. Which do you think is easier, calculating the signs of the first derivative, or just checking to see if f double prime is positive or negative? Just checking. I think this is easier to use. Almost surely the following story is false, but I find it funny, so I'm going to relate. So when the stealth bombers and the stealth fighters were being designed, what do you think they were trying to maximize? Stealth. And so the story goes that they didn't check to see if they were at a maximum or minimum for one of the things that they were doing, and they basically go like, we're over here playing. Almost surely false. But you need to check and see, am I at a maximum or minimum? For a lot of things, it's going to be clear. For the Farmer Brown problem, we're trying to figure out what is the optimal configuration to maximize the area for our cows, which is a very important problem at a school like this. Almost surely the answer we get is going to be the maximum and not the minimum. But for some problems, it's not so clear. And so you want to check and see, are we at a maximum or are we at a minimum? So let's quickly look at the Farmer Brown problem, because it is a nice way to lead into multivariable calculus and minimization. So we have x plus y is some fixed quantity. I'll do s for semi-perimeter. And you want to maximize x times y, which is the area. So this really does look like a multivariable calculus problem. We have two things to play with. But if we think about it, there's a really nice relationship between x and y. If I'm giving you the semi-perimeter, we can say, well, look, y is just equal to s minus x. So we can consider the function a of x is x times s minus x, or x times s minus x squared. What are the constraints on x? Where does x live? What's the largest x can be? What's the smallest? So 0 less equal to x less equal to s. We can have an extremely thin rectangle. Now, if you look at this, it should be clear that the boundary is going to be tellable for maximizing area. A of 0 is A of s is 0. And so when we calculate a prime of x to get the critical point, it's going to be s minus 2x. So a prime of x equals 0 implies s minus 2x equals 0. So therefore, the critical point is x equals s over 2. Technically, what should I do? Well, I just checked the boundary. The boundary is 0. Check whether or not it's a minimum or maximum. So if I look at a double prime, that's negative 2. All right, what the hell does negative 2 mean? It means I have a product that's going like this, so it's going to be maximum. I really should check the second derivative. But it's clear from this problem that this is going to be the maximum, not the minimum. Okay. Any questions on how to do the Farmer-Brown problem? So it turns out this is a really nice problem. I will talk about a quick generalization. Farmer-Brown has a friend. I believe the name is Arthur Curry. Anybody know who Arthur Curry is? Very good. So what is Aquaman trying to do? So Farmer-Brown is concerned with enclosing cows in a rectangular pen. What's Aquaman concerned with? Fish. So imagine Aquaman is trying to build something like this, and he doesn't have to worry about one side because that's the land. So he only has to put down 3 walls. And so now you've got y, and x, and you have x plus 2y is a primitive house. Do you see how you could solve this problem similarly to what we did before? And the area is going to be x times y. You could write x in terms of y or y in terms of x, substitute, go through and do the problem. There's a way to do it immediately. This is hard to see, but it's a beautiful way to solve this problem without doing any calculus. Because we already know the standard Farmer-Brown problem. Mathematicians are lazy. Whenever possible, we try to reduce something we already know. Imagine Farmer Brown, who's good friends with Aquaman, decides that he's going to build his cow pen right next to Aquaman. Okay? And so now Farmer Brown only needs 3 sides. Do you agree that whatever is optimal for Aquaman, if you just flip it, it's going to be optimal for Farmer Brown? We've now doubled the perimeter. It's now just the original it's now the original Farmer-Brown problem. What's the optimal shape going to be? Here we got x equals s over 2, so y equals s over 2. So in the original problem, it's a square. What's the original? What does this have to be? Square. So basically, if this is a square, then this has to be twice that. And I'll let you try to figure out how to write this up nicely. But this is a great example of how you can sometimes use an earlier problem to get a later one. This is much harder to see. But what we're doing is we're having Aquaman doing his thing down below while Farmer Brown does his thing upstairs. And whatever works for one is optimal, has to be optimal for the other. But this is a class of multivariable calculus. So let's see if we can do this using calculus. Did I just move the board back to where it was? Okay. So we have the constraint x plus y equals s. 0 less than equal to x, less than equal to x. And we want to maximize x times y. So what kind of shape is x plus y equals s? It's a line. So if I plot it like this, here is s, here is s, here is the line x plus y equals x. So I'm going to use g of xy is x plus y minus x. This is my constraint equation. So all of the candidate points satisfy the constraint. I am forced to stay on the constraint. Now let's calculate the gradient of g. So it's going to be the partial of g with respect to x, the partial of g with respect to y. What is the derivative of g with respect to x? So it's x plus y minus s. So what's the partial of g with respect to x? It's just 1. Right? What's the partial of g with respect to y? 1. So what this is saying is that at every point on this constraint line, the gradient of g is in the direction 1, 1. This line has slope -1. Right? If you look at it like this is perpendicular to the line. Okay? Let's look at f of xy. F of xy is x times y. What is the gradient of that? It's y comma x. So the gradient of f always going to be the same. So the question now is, what does the gradient of f represent? So we want to generalize what we did in one dimension. So if the first derivative is positive, that means we're increasing. If the first derivative is negative, that means we're decreasing. In one variable, the first derivative is kind of giving us information about how the function is changing. In several variables, we actually have something very similar. When we ask, what does the gradient of f represent? It's telling us how our function is changing. So if we think back to the tangent plane, f of xy minus f of, say, ax, ay, minus df, dx, ax, ay, x minus ax, minus df, dy at the point ax, ay, y minus ay. When we talk about what does it mean for the function to be differentiable, it means the tangent plane does a great job. I can write this again as this whole part here is just going to be the gradient of f dotted with x minus ax, y minus ay. This is giving us the change. The gradient of f times how much we're moving. If I have two vectors, how should I align the vectors so that the dot product is as large as possible? I mean, obviously, I could make one vector bigger and bigger and bigger, but let's say I can't do that. I want to take a vector, I want to take a change vector of a certain size, and I want to ask, how should I choose it? How should I orient it to make this dot product as large as possible? Where should it point? Parallel to it should point in the same direction as the gradient of f. Because if you have two vectors and they're both in the same direction, then our rule is it's the product of the lengths times the cosine of the angle. Right? The dot product is going to be product of lengths times the cosine of the angle. Well, if the vectors have fixed lengths, then the product of lengths part doesn't change. What does change is the cosine of theta. And so if I want to make this as large as possible, I want the cosine of theta to be as large as possible. We now have a geometric interpretation of the gradient of f. This is the direction f changes fastest. So if you want to figure out how should I move to see as much change as possible in F go in the direction of the gradient? What if you want F to decrease as fast as possible? Which way should you go? The opposite direction, because you would then want cosine theta to be -1. You want to go in the opposite direction. What if you don't want to see any change? Oh, but I like to move. You move perpendicular. So if you're perpendicular to the gradient of F, there's no change. So there is a tremendous wealth of information from looking at the gradient of F. It's telling us which direction do we go to see the greatest change. If we think back about what's going on over here, the gradient of G is the normal to the surface. Okay? If we are sliding on that line, x plus y equals f, we're falling down, we're moving at an angle. So we draw that down here. So over here, we're sliding down like this. Let's look at the gradient of f. We don't want the gradient of f to have any component in the direction we're moving, right? Because if the gradient had any component in the direction we're moving, we would see some increase. We can't be at a maximum. What direction do we need the gradient of f to be? Perpendicular. It's got to be in the same direction as the gradient of g. So the only way we can find a maximum or minimum for the formal ground problem is we need the gradient of f to be perpendicular to the direction of motion. We're moving down this line. Well, that means we have to be in the direction of the normal, the gradient of g. Because if we're in the direction of the normal, we have no movement in the surface. So we need grad f and grad g to be parallel. And this is going to lead to Lagrange multipliers, which we will do in great length later. So how many people here are potentially econ majors? Okay. So in economics, you often do look at Lagrange multipliers to try to optimize things. This is one of the things I want to make sure we cover. And so we know the gradient of G is 1, 1. The gradient of F is Yx. What's the only time for this problem that Yx can be in the same direction as 1, 1? What must be true about X and Y? If it's going to be in the same direction as 1, 1. Nope. They equal each other. So if X equals Y, then this would be X times the vector 1, 1. So the only way this can be in the same direction as 1, 1 is if X equals Y. Oh, well, if X equals Y, and they have to sum to S, they each equal S half. So when we do Lagrange multipliers later, we'll do this again. This will make a little bit more sense. This is a little bit of a coming attraction. And the real thing is this gives us a chance to really talk about what does the gradient of F represent? Which is more work? Doing it this way or doing it the way we did in Calc 1? I think it should be clear that this is a lot more work. It becomes necessary to do this as you get more and more variables because we have no choice. We can't just keep reducing it down. This problem is so simple that we can just say, oh, look, y, that's just s minus x. We can substitute that in. We can make it a one-dimensional problem. In general, we're not able to do that. So we do have to develop these techniques. And it all comes down to, geometrically, what does the gradient of f represent? And that's the high point for today's lecture. It's the direction where the function is changing the greatest. I'm going to do the question that was asked, and then I will talk a little bit about some other applications of tension. So before I turn to that question, any questions about what we've done? So the question is to find the highest point on the surface. So a lot of times, if I give you a function f of x, y, you can view the output as your height z. Maybe x and y are your locations on the surface, and z is going to be your temperature or your height. And the function that we're given, so we have z equals f of xy is 8/3 x cubed plus 4 y cubed minus x to the fourth minus y to the fourth. We want to know where is it largest. So the first question is this well defined? Do you think this function actually has a place where it's largest? What happens as x gets very, very large? Why? Yeah, x to the fourth, negative x to the fourth is going to destroy the 8/3 x cubed. And it doesn't matter if x is positive or negative, negative x to the fourth is always going to be negative. So if x is very large, this beats that. And if y is very large, the negative y to the fourth beats that. And so with a little bit of thought, you can show that if I choose some circle with a very large radius, if I go out far enough, this term is going to destroy the other terms. And the function is going to become negative if I go sufficiently far up. And so I do expect it to have a maximum. So how would I try to find where it's maximum? So what would I calculate? The postulate. So calculate the gradient of f, df dx, df dy. So I first take the derivative with respect to x. So it's going to be 8/3 times x cubed, so it's going to become 8x squared minus 4x cubed. And when I take the derivative with respect to y, I'll get 12y squared minus 4y cubed. And now you can begin to see why they had 8/3 x cubed. So this tells me how my function is changing. It tells me the maximum direction to go at any point in time to see the function increasing. So if my gradient is not 0, could I be at a maximum? No, because if my gradient is not 0, which direction should I go to see the function get larger? Gradient of f. Which direction should I go to see it get smaller? Negative gradient of f. So the only candidate where it could be largest is where the gradient of f is 0. So we need gradient of f equals 0, 0. So 8x squared minus 4x cubed equals 0. And 12y squared minus 4y cubed equals 0. And someone is being very kind to us in these functions. How would you factor 8x squared minus 4x cubed? What can you pull out of both terms? 4x squared. So this is 4x squared times 2 minus x equals 0. And over here I can pull out a 4y squared. I'll get 3y minus, 3 minus y equals 0. So I get x equals 0, 0, or 2, and y equals 0, 0, and 3. How many points do I have to check? So what points do I have to check now? 0, 0. X could be 0 and Y could be 0. What else? I want to go through it in a nice order so I don't miss anything. So I'm first taking X equals 0, then I take Y equals 0. Next I should take X equals 0 and Y equals 3. So I could check 0 and 3. I could take X equals 2 and Y equals 0, 2, 0. And I could take X equals 2 and Y equals 3. Is 4 points a lot to check? No. Do you think one of them has to be the maximum? So it turns out that there is a theorem in math that if you have a continuous function on a closed bounded set, where I have all the points, it is always going to take on its maximum or minimum. And so if I just show a really big circle, I know beyond that circle it gets very negative. At the point 0, 0, the function is just going to be 0. So I know it's going to be positive, at least at one point. And so it's going to be non-negative at least one point. So there should be a maximum somewhere inside. If X is really small, which is larger, X cubed or negative X to the 4th in absolute value? Say X is like 1 over a million. Which is going to be bigger, the X cubed or the X to the 4th? X cubed. So for large values, X to the 4th is bigger than X cubed. But for small values, X cubed, think of it as I'm dividing by a million. It's going to be smaller if I divide by a million more times. So if you choose X and Y to be very small, the function is actually going to be positive. So do you think 0, 0 is going to be the maximum? I don't think so. Because I can move just a little bit and make the function positive. So I think I can eliminate the 0, 0. You would actually just check and calculate. Which do you think is probably going to be the maximum? I think 2, 3. Because when I have a 0 here, notice how these two are completely independent. Right? There's no mixing of the x's and the y. I could actually view this as two separate problems. Where is the function 8/3 x cubed minus x to the 4th largest? Where is the function 4y cubed minus y to the 4th largest? Just view them as two separate problems. And then once you solve them, then bring them together. There's nothing that says you can't recast the problem to make it easier. This is clearly designed to be a multi-variable calculus problem. But can you read it as two calc 1 problems? Sure. I can view it as 8/3 x cubed minus x to the 4th and 4y cubed minus y to the 4th. Now, if I view it like that, those are much easier problems, and you can clearly see, oh yeah, I can plot these, I understand what's going on. And by splitting it into smaller constituent parts, the problem is going to be a lot easier. So by all means, feel free to try to do something like that. In general, you're not always going to be able to do that. When I was taking my oral exam to get my master's, you have to do various topics. One of the topics was complex analysis, and they asked me to do a certain thing called a contour integral. And I was supposed to know how to do it, and I knew how to do it. But interestingly, the night before the exam, as I was reviewing my notes, I saw one of my homework problems from college, where I realized that by being a smartass, you could actually convert it to a real problem and do it basically using one variable calculus. And so I asked them, do you mind if I use non-complex analysis methods on a complex analysis thesis? No, do whatever you want. And I was feeling really proud of myself. And then they rolled up their sleeves and started giving me generalizations of what I had just done to really push me. That was good. It was a nice experience. But they didn't care. Can you solve the problem? That's good. Now, we still want to make sure that you know how to do the contour integration because that's an important skill. But if you see another way to do that, there's good math there. We'll talk to you about that kind of math. If you can notice that this splits as a Calc 1 problem, that's tremendous. You've made the problem easier. for real Calc 2, Calc 1 problems, there's only one variable in play. For Calc 3, there should be interactions between the variables. Otherwise, it's just multiple Calc 1 problems. All right, so this is, I think, a good place to stop.